This begins the final chapter in my chemistry class, talking about chemical equilibrium. So, equilibrium suggests some kind of equality or balanced condition, and contrary to popular opinion, chemical reactions don't just go completely forward from beginning to end and that's it. Instead, just write as kind of a generic one here, so we've got coefficient, compound, compound. Our reactions can actually move back and forth between these two places. So our reactants don't all become products. So we have none of this left and all of this left. Instead, there is actually a back and forth motion between your concentration of products and your concentration of reactants that we can actually move back and forth between these two places. Some reactions, this balance point, this equilibrium position will be more towards this reactants side, where our reaction doesn't go very far. We end up with a high concentration of our reactants, low concentration of our products. So if you think about that, kind of like a seesaw. Sometimes our balance point has to be over here. Sometimes our balance point is down here towards the products, meaning that my reaction goes really far to the right. High concentrations of products, low concentration of reactants because my equilibrium was found back over here. Sometimes it's in the middle, equal amounts of reactants and products, but it varies on where this is. When a reaction can go backwards or forwards, we call that reaction reversible. So our equilibrium happens in these reversible reactions. All reactions, or nearly all, let me rephrase, reactions are reversible in some form or fashion. However, some reactions go really far to the right, really far to this product side, and it's hard to get them to go back to the left. Take, for example, a combustion reaction where carbon dioxide and water vapor escape into the air. Then it might be kind of hard to reverse our reaction. But this idea of reversibility is represented either by a double arrow like this, or perhaps more commonly by one arrow pointing towards the products and one arrow pointing towards the reactants, like this. Now, even though we say that all reactions are reversible, like I said with the combustion reactions, sometimes this is only in theory that our reactions are reversible. So since we have these multiple places where our balance, quote-unquote balance, can occur, it would be nice if we had some kind of measure, some kind of number that would tell us, did our reaction go way far this way, kind of in the middle? Where is this unchanging state? Well, that number is our equilibrium constant, this K. You've seen this K before when we talked about acids and bases, Ka, when we talked about how much an acid dissociated. To dissociate was to move towards the product side. So if we had a higher concentration of our products, we'd have a big K. Reaction shifted way far towards the right. So this should be kind of familiar to you. Our Ks are always, can't spell today, products over reactants. And in that, our coefficients always become our exponents. So products for this one would be concentration of C raised to the C power, concentration of D raised to the little d power, over concentration of A. Our reactants are on the bottom. Oops. So these are in fact being multiplied one by another. Reactants on the top and products on the top, reactants on the bottom. Man, that cold medicine's really scrambling my brains. Or at least that's what I'm going to blame it on. So notice that we're looking at concentrations of these amounts of products and reactants. We're not talking about grams or moles, we're talking about molarities. So those brackets are molarities. This means that we're interested in the concentration of products versus the concentration of reactants. And it should be stated that reactions don't hit this equilibrium, this balance point, and stop. Our products will continue becoming reactants. Our reactants will continue becoming products. Our reaction keeps going, but there is no net change in these concentrations. So the total amount of product does not change. The total amount of reactant does not change. So think about it in terms of kind of almost replacing. If one reactant molecule becomes a product, one product molecule becomes a reactant. So there is a net swap, if you will. So this equilibrium point is where we have no net change, but your reaction does not stop reacting. There is a continual change between those 2 points. Another thing that I should mention about this K is the fact that the K works only for a particular temperature. If your temperature changes, so too does your K. So for a new temperature, we would need a new K. And the reason for that, as we all know, increases in temperature tend to make things go faster, decreases tend to make things go slower, and it might alter my balance here. It might shove things farther to the right, make more products, or the flip side. Let me see. So, let's see how much time I've got. Oh, I got plenty. As we're talking about reactions, hopefully you would agree that as our reaction progresses, as we move forward, our amount of reactants, our concentration of reactants, has to decrease. It has to go down in order to make my products. So concentration of my products goes up during this. And again, equilibrium is when these 2 concentrations stop changing. No net change. So you still might have one particle go to products and another particle go to reactants, but our net change, our net concentrations of these amounts stay the same. We give this kind of a special name since it's this constant movement. We call it dynamic equilibrium. Dynamic meaning movement, equilibrium, balance point, equal point, if you will. So let's go and do a couple of these K's here. Let's talk about some of these numbers. Whenever we're talking about a reaction, it's important to note that since pure solids and pure liquids cannot change their concentrations, so pure solids and pure liquids do not go in KEQ because they cannot change their concentrations. Gases and aqueous solutions, however, can, so they do go in K. So, just to give you an example of a KEQ type problem, for example, let's say that we have a sample of bromine chloride gas that is decomposing into bromine, it's diatomic, and chlorine gases. And the problem tells me that after this reaction comes to equilibrium, so we put the BrCl in a box and we say go. And we find out when we take our measurements that at equilibrium, my concentration of BrCl was 0.45 molar. Our concentration of Br2 was 0.01 molar. And our concentration of Cl2 was also 0.01 molar. So let's find our KEQ and let's determine exactly how far to the left or to the right this reaction found equilibrium, whether the products or the reactants are favored. Now, if you look at these concentrations here, we could probably say that it looks like our reactants are favored, but let's get some more proof. So KEQ, we said by definition, means products over reactants. So my products are bromine and chlorine gases. Remember that coefficients become superscripts, exponents, 1 and 1, we're good, divided by my concentration BrCl. There's a 2 in front of my BrCl, so this is squared. Let's plug in our numbers. So, BrCl divided by our concentration of Alright, and I don't have my calculator sitting next to me. And this one is squared, so we're going to multiply 0.01 times 0.01 and divide that by our 0.45 squared, and we're actually going to get a value for this equilibrium constant. And we get an equilibrium constant of 4.94 roughly times 10 to the negative fourth for our KEQ. It has no units because it is a constant. If products over reactants is our formula, when I get a really small number like this, less than 1, substantially less than 1, that implies that our reactant amount down here was considerably higher than my product amount back here. So, again, this low number here, 0.00049, tells me that my reactants are favored. This reaction doesn't go very far. It doesn't really move towards reactants. Doesn't really move towards products. Whole lot of reactants left over. So this wouldn't be a very good reaction for any kind of industrial workings because, well, we just didn't go very far. But this is all there is to calculating KEQs. Products over reactants. Remember that any coefficients that you have in your equation become our exponents in our KEQ expression. Just to sum up, once again, don't forget that solids and liquids, these are pure solids and pure liquids. So things like sodium metal, water, they're pure. They cannot change their concentration and thus do not go in KEQ. Any gas or any aqueous solution does do in KEQ. These concentrations are not stopped, but instead this is a dynamic situation where we are still moving from reactants to products and back again, but there is no net change. In our next video, we'll introduce the idea of Q, our reaction quotient, to determine if my reaction is in fact at equilibrium. See you next time.